Hello everyone. Most developers skip JVM architecture because it feels confusing and too theoretical. But here is the truth. Java 8 changed how the JVM works internally and many developers don't even realize this. In this video, I will explain the JVM class loader in a very simple way. No heavy theory, no complex terms, just clear visuals and easy explanations. So let's first understand how a JVM loads a Java class. So before we go deep into individual part, I want you to see the JVM as a complete system. So at the top you can see the class loader. So this is the entry point. Every .class file, every Java feature first passes through here. So now let's see the middle section, JVM memory. This is where most developer gets confused. So in JVM memory, we have heap area, you can see here, and we have metaspace area, you can see here. So in Java 8, heap area does not have any change, but some classes related data which was stored in a separate space called perm generation was moved to a new area called meta space. So the classes which were present in perm generation was moved to a new area in meta space. So this change was made to fix out of memory errors that happened because perm generation has a fixed size and couldn't grow when needed, but metaspace does not have any fixed size and can grow as when needed. So at the bottom now you can see the execution engine. This is where the Java code actually runs. So when Java needs to talk with the operating system like file handling or native code, it goes through the JNI and native libraries. So don't worry about the whole architecture. We will explain each component in detail ahead. So now we will see the process of how a Java program is compiled and loaded into memory. So first we have the source file myprogram.java, which is compiled by a Java compiler into a bytecode file called myprogram.class file. So this .class file contains platform independent bytecode which is then loaded by the JVM by the class loader. Finally, the loaded class information and metadata are stored into a metaspace, a special area in JVM memory that holds this kind of data. So this process enables the JVM to manage and execute Java programs effectively. So now class loader is categorized into three types: loading, linking and initialization. Let's see each of them. So now let's see what is loading. So loading is a process where class loader reads the bytecode .class files and bring the class's definition into JVM memory. So you can see here loading is also categorized into three types: bootstrap class loader, extension or platform class loader, application class loader. So now let's see each of them in detail. So what is bootstrap class loader? So the bootstrap class loader is responsible for loading the fundamental Java classes that the JVM needs to start and run. It loads these core classes from a special file called rt.jar file which contains the essential runtime libraries. Examples of these classes include java.lang.string, java.lang.object, java.lang.thread and java.lang.arraylist and many more. So these classes are building blocks for every program. So the bootstrap class loader also loads other internal classes from the JDK. So now let's see what is extension or platform class loader. So the extension class loader loads extra classes that adds new features to the basic platform. These extra classes are called extension classes. Usually it looks for these classes in a special folder named ext or library inside Java installation. It also loads extension classes from other folders, which helps Java to do more things than the core basic Java features. So now let's see what is application class loader. So application class loader loads the Java classes you create from your program. It looks for these classes in a place you set called the class path. This means it can load files from the folder of your computer or from any special jar file that you add to your project. It can even get the classes from the internet or the network if needed. For example, if you write a Java class called myprogram, this class loader will find and load it so your program can run. So now we have completed the loading part. Now let's move to linking part. So what is linking? Linking is the process where the JVM checks, prepares and connects the loaded classes so it is ready to run. So as you can see here, linking is categorized into three types: verifications, preparation and resolution. Let's see each of these topics in detail ahead. So in verification, the JVM checks that the class file is genuine by looking for a special signature at the start and make sure all the parts inside it are in the correct order. If anything is wrong, it rejects that file. So in verification, the first part is it checks the class file format. What does it mean? The JVM checks that the class file is genuine by looking for a special signature at the start and making sure all the parts inside it are in the correct order. If anything is wrong, it rejects the file. So next is it checks the bytecode. What does it mean? The JVM checks the bytecode to make sure the program instructions are not broken or damaged. This helps to prevent crashes or error when the program runs. So next is it checks semantics. What does it mean? The JVM also checks that the code makes sense and follow Java instruction. This means it verifies things like using variables correctly and calling methods the right way to make sure the program will work as expected. So it ensures class file is valid and safe. So now let's see what is preparation. In preparation, JVM sets up memory for all the static variable in the class. It also assigns them default values like 0 for numbers, null for objects, and false for booleans. This gets everything ready before the program starts running. So no user code execution is started yet. So the next is resolution. What does it do? It resolves symbolic references. What does it mean? When the JVM resolves a class, it finds the real location for all the names used in the code, like the class name, method names, variable name. Instead of just using their names, means symbols, it connects them to the actual place in memory. And it also loads any other classes that this class needs to work properly. This way all the parts of programs are linked together and ready to run. So till here now, no user code is executed yet. So till now we have seen here loading and linking. Now let's move to initialization. So now let's see what the initialization does. So it first executes the user code. So what does it mean? When the JVM initializes a class, it starts by running the code you wrote. Second, it assigns static final field. So it sets value for constant variables, static final fields. Third, it runs the static initializers. So what it does, it runs any special setup code called static blocks. For example, if you have a static block that prints a message, it will run during this step. This makes sure the class is ready to work properly. So user code execution begins in initialization process finally. Let's deep dive into part 2 of JVM architecture, that is JVM memory. So without wasting time, let's get started. So now let's see the first component, heap memory. So heap memory is the runtime memory area where all Java objects are stored. It is shared across all threads in JVM. If an object is created using new keyword, it goes to the heap memory. So heap memory is divided into two categories, young generation and old generation. You can see here it is divided into two categories. This is young generation and this is old generation. So what is young generation? Young generation is used for creating new objects. So all newly created objects are first stored in the young generation. So most objects are short-lived, so JVM keeps them into young generation. Now let's talk about hidden space. It is known as object birthplace. So whenever we create an object using new, it is allocated in hidden space. So here it is allocated. So next let's talk about survival spaces, that is S0 and S1. So it is also known as object survival test. So objects that are still in use are moved to survival spaces and it checks whether an object should live longer or not. Now let's talk about promotion. So promotion is nothing but moving to old generation. So objects that survive multiple times in young generations are promoted to old generation. So you can see here the objects which are created in hidden space and that are survived for longer time is getting promoted to older generations. So from younger generations, objects are getting moved to old generations. Now let's talk about old generation. So old generation is a place where objects are lived longer period of time. So old generation stores long living objects. Examples are singleton objects, cached objects, objects used throughout the life cycles are being lived for longer period of time. So most objects die young. So JVM optimizes memory by sharing short-lived and long-lived objects. So that is all about heap memory in JVM. Now let's move to the next part, metaspace. So before moving to metaspace concept, let's see a concept called perm generation, which was introduced before Java 8 version. So perm generation concept comes inside heap area. So in heap area we have young generation, old generation, and the third is the perm generation, which we are going to see now. So now let's see what is perm gen. So perm gen is special memory area in JVM before Java 8, which is used to store class related information and which is managed by JVM garbage collector, and it does not store normal Java objects. So what does perm gen store? It stores class metadata like class structures, fields, method metadata, runtime constant pools, and static variables. So why does perm gen existed? To keep class metadata separate from objects and to improve JVM performance. So now let's see PermGen JVM options. So PermGen memory tuning options are below. -XX perm size, which means you need to pass the initial PermGen size. -XX max perm size. So you need to pass maximum PermGen size. So if you want to tune PermGen memory, you need to pass two parameters. First is the initial PermGen size and second is the maximum PermGen size. So now let's see what is the common PermGen error which we get. So the common error which we get is java.lang.out of memory error, which is the perm generation space error. So when does it occur? It occurs when too many classes are loaded and when perm generation size is too small. So this error is very common in web applications. So now let's see why perm generation was removed. So the reasons are it has fixed memory size, manual tuning is required, frequent out of memory errors and difficult garbage collections. So now we have completed the heap area, which consists of young generation and old generation. PermGen also we have completed, and now let's move to metaspace area. What is metaspace? Metaspace is memory area introduced in Java 8 and it replaces perm generation and store class related metadata, and it is allocated in native memory. You can see here it is allocated in native memory, which is outside heap memory. So what does metaspace store? It stores class metadata, informations like class structures, fields, method metadata, runtime constant pool, static variables, and JVM internal metadata. So why metaspace was introduced? It was introduced to remove perm generation size limitations. We know perm generation was having size limitations. So metaspace does not have any size limitations. It grows when required. It helps to reduce out of memory errors. It helps to simplify JVM memory management. So metaspace JVM options. Metaspace tuning options are below. -XX metaspace size, which means we need to pass here the initial size. -XX maximum metaspace size, which means we need to pass here the maximum size, and also the maximum size is optional here. So metaspace out of memory error. So error which we get in metaspace is java.lang.out of memory error. So this error occurs when too many classes are loaded, class loaders are not released, maximum metaspace size is reached if it is set. So this error is less common but still possible. Now this is just a comparison chart between perm generations versus metaspace. So in perm generation it was introduced before Java 8, metaspace was introduced in Java 8 and later. It was a part of JVM heap and metaspace uses native memory. So perm generation has a fixed size where metaspace dynamically grows. In perm generations, manual tuning is required, while in metaspace, minimum tuning is required. In perm generation, we get out of memory errors frequently, but in metaspace, we rarely get out of memory error. So guys, till now, if you really found this video helpful, please do not forget to subscribe my channel so that you will never miss an update for my upcoming videos. Now let's go to JVM stacks. So JVM stack is created per thread. Each thread has its own stack. Stack stores method calls. For each method call, one stack frame is created. So stack frame contains local variables and method results. Stack works in LIFO order, last in first out. Last called method finishes first. Stack is thread free. One thread cannot access another thread stacks. So in stacks, memory is cleaned automatically. No garbage collector is needed. So in JVM stack, the common error which we get is stack overflow error. When does this error occurs? It occurs due to deep recursion, too many methods called. So we have completed all about JVM stack. Let's move to next topic. Let's see PC register now, which stands for program counter. PC register keeps tracks of which instructions the JVM should execute next. Each thread has its own PC register, so multiple threads can run independently without interfering with each other. The PC register stores the address of the current instructions, and after execution, it moves to the next one. For native method, the PC value is undefined because native code runs outside the JVM. So the overall, PC register acts like a pointer, helping the JVM know exactly where it is during execution. Now let's see native method stack. So native method stack is used for native methods. It works with Java native interfaces. It stores execution of C or C++ code. It is separated from the JVM stack. It is platform dependent. Platform dependent means a program can only run on a specific operating system or hardware. It is not used for normal Java methods. When Java call native code, execution moves to native method stack. So this is all about native method stack. Today we are going to see the third part of the video, execution engine, along with other modules like native method interface, native method libraries, code cache, JIT compiler. So now let's start with interpreter, which is the first component of execution engine. So after class loading and memory setup, the JVM needs to execute the code. So the interpreter does this by reading the Java bytecode and executing it line by line. Now let's see how an interpreter works. So Java source code is compiled into bytecode. The interpreter reads one bytecode instruction and it converts it to machine code. It executes it immediately and then it moves to the next instruction. So JVM bytecode with the help of JNI, Java Native Interface, is getting converted into machine code. Now let's see below points. It reads bytecode line by line. This we have seen already. So second point is it executes instruction one at a time. What does it mean? The interpreter does not convert the whole method at once. It executes one instruction at a time again and again. That's why it's called interpretation, not compilation. So next, it is quick to start but slow for repeated code. What does it mean? The interpreter is quick to start but it becomes slow when the same code runs again and again. Next, it is less efficient for frequently run code. What does it mean? The interpreter is less efficient when the same code is executed frequently. Now let's understand the JIT compiler, which is also called just-in-time compiler, which is part of JVM execution engine. As we saw earlier, the interpreter executes bytecode line by line, which is slow for frequently running code. So to improve performance, JVM uses JIT compiler. So JIT compiler improves performance by compiling frequently used bytecode into fast native machine. So the hot code, which is frequently executed with the help of JIT compiler, is moved to native code, and this native code is then later stored in the code cache, that is native memory. So now let's see below features of working of JIT compiler. So first is it speeds up the frequently run code. Next, it compiles only hot code at runtime. What does hot code means? Hot code means frequently executed bytecode. So it compiles only frequently executed bytecode at runtime. So this hot code is sent to Git compiler. So Git compiler converts this bytecode into native machine code. This compilation happens at runtime, that's why it's called just in time. So after compilation, the native machine code is stored in code cache, native memory. So code cache is a part of native memory. JVM directly executes this native code next time. No interpretation, no recompilation. So this is what this line means, stored compiled native code in code cache. So friends, till now if you enjoy watching my video, please do not forget to subscribe my channel. So now let's move to next topic. Now let's see what is code cache. So code cache stores JIT compiled native code from frequently executed bytecode. So frequently executed bytecode with the help of JIT compiler is moved into code cache native memory area. So now let's see what are the features of working of code cache. So it stores frequently compiled native machine code. So where does code cache exist? It exists in native memory outside Java heap. It allows faster execution of hot code. This we have already seen. Next, it improves repeat performance a lot. JVM avoids reinterpreting code by reusing compiled machine code from code cache. What does it mean? So JVM runs compiled code from code cache instead of interpreting it again. So this is all about code cache. Now let's see what is garbage collection, GC. Garbage collector automatically frees up memory by deleting objects that are no longer needed. So this is a diagram of JVM memory where we can see unused objects are being deleted by garbage collection. So how does it delete the object? It finds unused objects in the heap. So how garbage collection find these unused objects? So suppose the references which are set to null, like for example, suppose we have string s is equal to new string of Java and that s is pointing to null. So since s is pointing to null, the object is been garbagely collected. So second, when any method execution completes, it is eligible for garbage collection. So it deletes those unused objects to free up memory. It reclaims memory so JVM can reuse it. What does it mean? It means the JVM frees the heap space used by unreachable objects so that space can be reused for creating the objects, and which helps to prevent memory leaks. So this is all about garbage collection. Now let's move to next topic. Let's see Java native interface now. So JNI allows Java applications to interact with native code written in languages like C or C++. So JNI acts as a bridge between Java code and native code. So this JNI, it acts as a bridge between Java and the native code. So what are the features of JNI? It invokes native functions from Java, example C or C++. It calls Java methods from native code. It passes data between Java code and native code. It accesses platform specific features and libraries. So that's all about JNI. Now let's see native method libraries. So native method libraries are collections of native code written in languages like C or C++ that can be loaded into Java applications for executing platform specific functions. So Java program with the help of JNI goes to native method library. Now let's see the features of native method library. First is it extends functionality beyond Java. What does it mean? It means Java uses native code to do extra work that Java alone cannot handle. Next, it accesses platform specific resources. What does it mean? It means Java talks to Windows, Linux or Mac operating system features using native code. Next, it improves performance using native code. What does it mean? Native method interface improves performance by allowing Java to execute critical code directly into faster native languages like C and C++. So guys, if you really found this video helpful, please like the video, share the video to your friend circles and subscribe to my channel. I have given complete Java playlist in the description box, and if you have any doubts regarding this video, you can put your doubts in the comment section. So whenever I get free times, I can look into it and solve your queries. Happy learning with Java and see you in the next video.